we started talking about rotations a little bit. If you remember that, we realized that for a one-dimensional periodic domain, so if you're in one dimension, and after moving by L, you get back to the same place. Then that basically tells you you're basically on a circle. Right. So that's probably a good way to motivate this. Right. So periodic domain recall. If you have a periodic domain, meaning x plus L in 1D equals to x, and you find that that's the same as a circle, where now if I let phi be my angle, right, this is the angle, then of course phi will be equal to phi plus 2 pi. Okay, that's on a circle. So this doesn't map between these two because if you are on a circle versus if you're on a periodic domain, this is 0, L, 2L, 3L, 4L, and so on. Each of these guys can be mapped into the circle. Right? So you start from 0, go all the way to L. So that means basically that the radius, 2 pi r is L. So radius is 2 pi over L. Right, so basically you're on a circle of radius 2 pi over L. So if you go one way, so this will be L, right? From 0 all the way to L. And then you can do it again and again and again, but it's the same thing. So that's basically the same. That's basically the same thing as this.
So radius should be L over 2 pi.
Inverse.
Sorry, thank you. Yeah. So this is a good This is a good kind of jumping off point to consider circle the rotations on their own accord. So we're going to start with 2D rotations. And what we're going to discover is that it's actually very similar to the Fourier. So eventually what you discover is that this gives you the Fourier series. Right? So this periodic domain is very much related to the Fourier series. And what we're going to discover is that's going to be recovered in the circle, in the 2D rotations case. So I think I've already mentioned that if you can extend this to higher dimensions. It's just harder to draw. If you have one more periodic dimension, for example, then it'll be a donut, right? So basically you have the extra dimension that is also periodic, so that you need two circles. So circle times circle is basically a donut. And then if you go higher dimensions, you get higher dimensional tori. So you can continue this, but we won't. We have done it for the periodic domain, but I've not drawn the pictures for higher dimensional donuts and so on. Right? It's a little bit more difficult to draw, so I won't try. But the idea is very similar. Okay, so let's start with two-dimensional rotations from the very beginning, because this is going to lead up to the three-dimensional case, which is quite a bit more complicated than the two. So I thought I'll start here as a warm-up, right? So if you've taken my quantum field theory class, you might be, or taking my quantum field theory class, you might be a little bit, you might you might see it, you've seen it before, right? So bear with me. So basically in 2 dimensions, you can write down the rotation matrix directly. Cosine phi, sine phi, sine phi, cosine phi. And what this does is that it applies to a 2-dimensional vector, and it literally just rotates it, right? So let's actually verify that. So how do you figure out the rotation matrix? Well, you know that the rotation, as written here, is a matrix. So it's a linear operator acting on this space. And we know by now, or hopefully you've learned by now, that if you want to figure out how a linear operator acts, just act it on all the basis vectors and figure out what it does. So here's one basis vector, right? So this is the one axis, this is the second axis on 2D. And so this first axis, let's call it E1, is just 1, 0, right? And we know let's make it a little bit bigger so I can draw a triangle. So this guy is 1. And I want to rotate it by an angle phi, right? So what does that mean? I want to do this, something like this, right? And this is angle phi. So now I know what the x and the y is, and it's given by, this guy is given by what? It's just sine phi, because this length is 1, right? I'm rotating. And then what is this? This is cosine phi. Okay? So that's the first basis, which means that I want r hat phi acting on the first basis to give me, maybe I should put a transpose. Usually we write it as a column vector. So we want it to become cosine phi and then sine phi. Right? That's the first axis, first basis. And for the second basis, you start here. Okay, you start here. This is length 1. And now you want to rotate it by phi. Okay, so this is phi. Okay, I'm going to erase that. Phi. And again, you have the y component and the x component. But now the y component is cosine phi. Right, I hope you know your trigonometry, so I'm going to just write down the answer. And then for this guy, the length is sine phi, but remember it's pointing this way, so it's minus sine phi. Okay. And the way trigonometry works is that if you do it for just a acute angle, it's going to work out for the other quadrants as well. Okay. So once you figure out the trigonometry for one, trigonometry itself will take care of the rest of the, meaning if the angle is bigger than pi over 2, or here, this will take care of itself. But what it means here is that if E2 is 0, 1 transpose, then we figured out from geometry, right, that this acting on E2 is equals to minus sine phi and cosine phi. Okay, and so once you have figured this out by geometry, then this is fixed. Okay, I should let you think about it yourself. But at this point, it should be almost immediate. You should be able to see almost immediately, right? But yeah. So by now you should know that once you have defined how your linear operator acts on the basis vectors, you're done. Right? That defines the linear operator. And I claim that in this basis, in the E1, E2 basis, that is the rotation operator. Okay? And one of the key properties of this guy is that the rotation's angle add. Right? So you're going to calculate explicitly, probably in your homework, is that if you take, it's geometrically quite obvious, right? If you take one vector and you rotate it by phi, and you rotate it again by phi prime, you're going to get simply phi plus phi prime. Right, that's geometrically quite obvious, but of course it's good to check the math. And this tells you that if you want to preserve this product rule, there are ways to do this that don't just involve the matrix, right? So this is something that we will do quite a bit as time goes along, and I'll motivate it as we go along. But for now, let's observe the following fact. If I map, if I define a function of these matrices, so this is now a function of the matrix, the rotation matrix, and I call this e to the I phi, okay? Then you notice that it also preserves this product rule, okay? Meaning, so what do I mean by that? I take the function of r phi and the function of r phi prime. So if it's going to preserve this product rule, it better give me back the function of r of phi plus phi prime. Okay? That's what it better give me. Now, is it true? So that the question is it true? And the answer is definitely. Why? Because these two guys are just e to the I phi, and this guy is e to the I phi prime, and this guy is just e to the I phi plus phi prime. Right? And of course this is true because the exponentials, the exponentials add. And why is that so? Again, in fact, by geometry, you know that this has to be true because we're just dealing with complex numbers. And so, in fact, if you remember your complex numbers, there's in fact a direct map because instead of one axis and two axes, you call it the real and the imaginary, right? And so e to the I phi is just a complex number with length 1 and angle phi, right? With respect to the real axis. And what you discover is that complex numbers are useful. One of the reasons why it's useful is, in fact, because addition of complex numbers is like adding vectors, and multiplication of complex numbers is like rescaling and rotation, right? Are you guys familiar with this? Multiplication by complex numbers is rescaling and rotations. Okay. So you might wonder why am I saying this? So I'll get to this in a little bit. But this is the simplest example of what's called a group representation. One of the simplest examples. So it turned out that rotations is a group. I'll define what a group is in a little bit. And in fact, when you define a function of the group elements, whatever group you have, if you define a function in such a way that it preserves the product rule, meaning the function of one group element times the function of another group element gives you the function of the product of the two group elements. That is what it means to be a group representation, a product preserving function. That's basically what it is. Maybe I should write it down, right? So let me write it down in a more abstract way. G1, G2 equal to D of G1 times G2. Right, so function of group such that the product rule is preserved. Actually, I should also say usually the function maps it to a linear operator. So, yeah, so let me say, so D is a linear operator. Otherwise, the more general terminology is called a homomorphism, but I don't want to go that because we're physicists. We don't have to be too. In physics, we tend to be more pragmatic. So we don't have to be the most abstract possible. We tend to just be more pragmatic. Whatever is useful for physics, we use it. Yeah. But the mathematicians, of course, they do it for their own sake. So they are trying to be as general and as abstract as possible, which is of course very, very important for its own sake. But yeah, not us. We are just practitioners. Okay, so yeah, again, if it preserves the product rule, it's called a homomorphism. But for us, it's always a linear operator. So that's called a representation. Now, this is just ordinary rotations, right? So this should be familiar. It's just geometry. I take my rotation matrix and I apply it onto my vector, and that is something that hopefully is familiar. But now I'm going to promote it. This is the warm-up, actually. I'm now going to promote it exactly to a linear operator. But now my linear operator is going to act on position eigencast. I'm going to drop the r hat for now because it's just a rotation. And now I'm going to define it to be acting on the position eigencat. Just like, if you remember, we did it for translations, right? So you remember that we talked about translations by first defining a translation operator acting on the position eigencat. In this case, you can think of it as translation operator, but translation on a circle. Okay, but because we're not going to talk about the radius for the time being, I'm going to suppress the r, right? So you can think of this as r psi, we're in 2D, so there's only two coordinates, right? But I'm always going to just ignore the radius for now, right? Of course, the real problems usually have more than one dimension, but for now, we don't need to care about this. But what is that? This is just psi plus phi, right? So position eigencat, where psi is the angle. And that's the definition, right? D acting on psi is just going to rotate it by phi. And of course, we're going to have the identity. Identity doesn't do anything to it. And let's see what happens when we try to find its conjugate, okay? So what we're going to do is we're going to realize that something like that is very much like the position eigencats in 1D, right? So you should expect that basically this is delta function of phi minus phi prime. So you can think of this as translation symmetry. In a periodic domain, or rotation symmetry. Right, so I think we had a few questions about this the last time, right? So compared to a box, you compare a box to a periodic domain. If you are in a box, you can tell how close you are to the wall, right? So the wall defines for you where you are in position. But if you're on a periodic domain, there's no way, there's no distinguishing boundary, right? It's just that it's like a circle. You can rotate your circle all you want. You will not be able to tell where you are on the circle. as long as there's nothing else on the circle. But this is no other way for you to tell that where you are. So circle and a periodic domain are all symmetric spaces, very symmetric spaces. Either you can think of it as translation or rotationally symmetric. And so with this, you can basically show that this guy better be unitary, right? So remember that is the analog of why we know that translation in an infinite space or a periodic space is unitary, is because there's no privileged set of coordinates, no privileged set of bases. So let's do it. So the first thing to recognize is the following, right? So what is, for example, with psi prime? So psi prime is an angle. D phi dagger. Well, this is equals to, remember, this is d of phi acting on psi prime dagger, right? And this translates, or if you like, rotates the position by phi dagger, and this is therefore just psi prime plus phi. Okay, and then that we can just act it on psi dagger, phi, d phi dagger. I'm sorry, psi prime d phi dagger, d phi psi. Well, I know how to do this, so I don't have to write it down again. So this is now just the bra and the d dagger is, we found out, psi prime plus phi. This guy we know already is psi plus phi. Okay, but then according to this delta function normalization, you get delta function of psi prime plus phi minus psi plus phi. Okay, and so therefore the phi's cancel out, and you get delta function of psi minus psi prime, or psi prime minus psi, and that is just equals to psi prime identity psi. Okay, hope you guys can see. Let me write it again over here. Yeah, so again, what have we shown over there? We've shown that psi prime d phi dagger d phi psi is equals to psi prime plus phi psi plus phi, but the phi's cancel out in the delta function. Oops. And therefore this is just psi prime identity psi, right? And because of that, psi prime and psi are completely arbitrary. Yeah? So because they're completely arbitrary, that means that d phi dagger, d phi, in fact is the identity. So therefore D is unitary. And that's not surprising. It comes down to just the fact, again, that rotational symmetry on a circle is very much like translation symmetry in a periodic domain. Right? So I claim that this is just consequence of rotational symmetry. Okay, and in this one-dimensional case, it also commutes. Okay, so let's do that as well. So D also commutes. So what do I mean by that? D phi prime acting on psi. Well, I think it's quite clear that this will become sine plus phi prime, regardless of how you do it, right? Just because rotation doesn't care about it, it's just an addition. So therefore, this is just equal to d phi prime, d phi acting on psi, they commute. Now, these two things should tell you, unitarity and commutativity tells you that the generators also commute just like in translation, right? So recall, for translations, we have e to the minus I d dot p, and because translations commute, right? D and d prime, when you commute the translations operator, you find that it's zero. It's just, again, this is just geometry. Just like this one is just geometry. But the consequence of that is that the momentum operators commute amongst themselves. Okay. And in this rotation case, it's actually even easier. It will turn out that there's only one generator, and you will discover that and let's in fact see how it works out. Okay? So now let's come back to, so in fact, to figure out the generator of rotations, let's in fact revisit the original matrix representation itself. So R phi is cosine phi minus sine phi, cos phi. Okay. And so remember that this is supposed to be e to the minus I phi times something. That's just what we expect, right? So this is what we expect. Now, how do we figure this out? If this is true, then we should expect that this is identity, 2x2 identity, minus I phi j hat plus higher order terms, right? So the exponential form, remember we've already argued that anything that is continuously connected to the identity should take this form. And in this case, it's two-dimensional rotation, which is certainly continuously connected to the identity. Why? If you don't rotate, then that's the identity. So you know that it has to be true, right? So the exponential form has to be expected, except that, how do you know it's phi j hat, right? So the way to do it is actually, you can show it explicitly, right? In this case, you can show it explicitly. And so let's first make a guess. What is phi j hat? So you take this guy. So that's one way to, the other guy is just to tailor expand this guy, right? So remember that cosine phi is 1 minus 1/2 phi squared plus higher order terms. So if you start to rotate from 0. And sine phi is phi plus minus, phi minus 1 over 3 factorial. This is in fact true. Yeah, and therefore, in fact, J is as given, and we have just figured out the generator of two-dimensional rotations. And in fact, there's only one. There's only one of them. Any questions at this point? Yep.
So, for higher dimensional rotations,
Yeah.
The generator can be represented by Lamish level. The generator only can be represented by polygons.
Yes, in 3 dimensions, yes. It is in fact representable by Lamish-Vita. In 2 dimensions, in a certain basis, this is actually sigma 2. If you look it up, it's sigma 2. But I prefer not to write it that way because it's a little bit confusing. You are basically specializing to a particular basis. But rather, I want to just emphasize that if you write down the rotation matrix, you can just figure out what the generator is just like that, right? Without specializing, without saying that, oh, that's sigma 2. But well, why is it sigma 2, right? That connection is a little bit, I claim it's a little bit confusion. Yeah. Yeah, but I don't know if that's your question. I think your question is more the difference is in 2D and 3D, right? In 2D, it's Lamish-Vita in this sense. In 3D, it's also Lamish-Vita, but there are 3 of them, right? So you have to be a bit careful as well. There are 3 of them, right? Yeah. Yeah, okay, good. Okay, so the next thing to do is to generalize this to the case where D is no longer, R, we're not just discussing R itself. R is you can think of it as the original definition of what rotation means. But remember, we're doing quantum mechanics, right? And in fact, this is a good time to talk about representation theory, right? So why did I just mention to you there are ways to map group elements, rotation is a group, to linear operators. And in physics at least, one of the greatest motivation, one of the biggest motivation is because we want to apply the notion of symmetry to quantum mechanics. So when you have rotation symmetry, translation symmetry, all these things, how do you bring over these notions to the context of quantum mechanics? That means you have to find a way to convert your rotation matrices or whatever the translation into linear operators acting on your Hilbert space, right? So that's the key point. Yeah. So why group representations? And I do realize I haven't defined a group yet. So, but let me just write this down first. Okay, and the answer is that this is to bring over or realize, maybe that's the way people say it, you want to realize symmetry transformations on quantum systems. Or I should say to realize we have to convert or map, what do we want to use the word, what do we want to use, convert group elements to linear operators acting on the Hilbert space. The Hilbert space that your quantum system lives in, right? Because what acts on the Hilbert space are linear operators, so there's some way, you have to find some way to do that. So implicitly, we've already done that for translations. I didn't quite use those words, so at least I didn't emphasize that. But we're going to get a little bit more involved now, so I think it's a good place to start talking about it in this language. Right? So basically, for rotation, for groups, there are first a few axioms, not like it's actually much simpler than the linear algebra, because there's only a few. There are only a few axioms which I'm going to write down over here. So, firstly, what's a group? So if you have two elements, so let me just call it G1, G2, and so on, group elements. Then the first thing is closure. Okay, you've got to make sure that when you multiply two of them together, it gives you another group element. So in our case, for example, R phi times R phi prime is just R of phi plus phi prime, right? And so, therefore, they are both, left-hand side and right-hand side are both group elements. Associativity is the next one. So, doesn't matter how you multiply them, which order you multiply them. Sorry, let me say it properly. Which sequence, that's better word, but the order matters. Don't do 3 to 1 and think that it will give you 1 to 3. But what I mean by the sequence is that you can multiply 2, 3, and then 1 to the left, or you can do 1, 2, and then multiply the result to 3, and they are the same. Okay, so therefore you can simply write it as G1, G2, G3 without any ambiguity. Certainly it's true for our group, for our 2D rotations. It's true for any rotations actually, because remember that matrix multiplication is associative. So at least for this point, it's immediately clear that higher dimensional rotations are associative as well. So this associativity is immediately satisfied by all rotations. And then finally you have third thing is you have identity. Usually people call it E. So E times anything gives you back the same thing. Maybe I shouldn't call it G, let me call it G1 or GI. I just don't want you to be confused with example. EG is example, right? So EGI is equal to GI. Okay. And this is the same, so the left and the right inverses are the same. Although that has to be proven, but let me just tell you that it is true. And then finally, there is an inverse. Okay. So for every element, for every element, there is a inverse. Right, so I have to talk about the identity first. Right? It has to give you back the identity when you multiply. So for our case, identity is just a 2x2 identity matrix. And the inverse rotations, if you remember, well, in our case, two-dimensional rotation, there are different ways to write it. In your homework, you will discover that there are multiple ways to say this. It is either just flip the sign of this, or take the transpose of R5, and all of them will be equals to R inverse. Okay, so the inverse exists as well. So we're going to talk about it one more time when we talk about three-dimensional rotations. But here's basically a warm-up, so to speak. Okay. So now, we know the generator for the defining the two-dimensional rotation matrix, and we now know that these rotations are a group because they satisfy these 4 axioms. So now we're going to map it to our linear operator, right? And we're going to see what happens then. And then we'll take a break. So what we're going to say is that now we're going to map my rotation matrix into a linear operator, right? But we've already kind of done that, right? This is what we call D of phi just now. But now, because we know that there's only a single generator, we know that it has to take e to the minus I phi j. And so it is this guy that we act on psi, the angle psi, to give me psi plus phi. Okay? But because e to the minus I phi j is unitary, we just proved it, we now can identify yet another observable. J must be permission. So what we're about to discover is that this is like the position eigencaps. In the sense that, at least conceptually, there are the infinitely sharply localized states at each angle, right? Now we're going to ask, what is the corresponding kind of momentum eigenstate? That's not how this is actually the angular momentum, right? So this is the beginning of, we can discover M, where Jm is M times M, now the angular momentum eigenstates. Okay, and I just want to lay out the analogy here, right? Position, angular momentum. Previously we had x, so x is the position, and then k are the linear momentum eigenstates. Maybe I should say these are the angular positions, right? Just to make it more precise. Whereas these are the actual Cartesian position. And the corresponding linear momentum, whereas these are the angular momentum. So I haven't really worked them out yet, but you should already expect that just by virtue that J is Hermitian, and I haven't really told you much about it, but just from the fact that J is Hermitian, you know that they must have a complete set of eigenstates. So after the break, we'll talk more about that. Any questions? Okay, see you guys in 10 minutes. So, as I mentioned, the generator is Hermitian. So in fact, let's see it explicitly using the generator of the rotations in 2 dimensions, right? So we found out that this is equal to cos phi minus phi sine phi, and then minus sine phi cos phi. And we found that in this case, J hat was I, or maybe minus I, by Vichy beta. Okay, and what you find is that this guy is antisymmetric and real. So therefore, when you take, you can easily check that this guy is Hermitian. J hat dagger is the complex conjugate, so it's plus I, but then epsilon dagger, epsilon is real, so this is just transpose, because it's real. There's no complex conjugate to do. But because it's antisymmetric, this gives you minus I epsilon. Okay, so the minus comes from the fact that this is antisymmetric. So therefore, you get back J hat. Right? So you should be worried if it doesn't turn out to be a Hermitian, then how can I claim it to be? How can I claim that when I map it to the linear operator, J is Hermitian, right? So this should be Hermitian. Now this is just a check, so to speak, right? So the generator is Hermitian. So how do we figure out what J is? So there are different ways to represent it. And what we're about to discover is one of the representations is what we call angular momentum. Okay, this is probably not how you saw it in undergraduate quantum mechanics, but I'm going to show you. This is the kind of the more Hilbert space, just from Hilbert space itself, how to get it, right? So what do I mean? So what we're going to do is the following. We're going to do something very similar as we did for translations in space. So what we're going to do, let me erase this because I need some space, is to first work it out in position space and see what that tells us about J. Okay. So what do I mean? So that's why we need this. So firstly, let's take my rotations and then apply it to x1, x2. So these are just my Cartesian coordinates, right? But now I know that this is I minus, and then minus I, actually, let me just write it as, actually it's minus I phi, and then multiplied by my v beta, right? Minus I my v beta, and all of it are acting on x1, x2. Okay? And so let's write it out a bit more explicitly. So this is just x, and then now I have minus, because I have minus I, and so let's sign errors. Yes. This would be minus 5, and then my v beta acting on x. Okay? So we're going to assume that phi is a very, very small angle from now. And now let's consider the following thing. And you should recall what we did for translations. It should jog your memory. So what do I mean? So let's kind of rotate my two-dimensional position eigentemp, right? So we know that if you look at cylindrical coordinates, that amounts to just rotating these phi's, right? But now I need to put back my r and phi, because now I want to use the Cartesian representation of this. But we know what it does. It just rotates. It just rotates these positions by rotating their phi. But now we're going to go back into Cartesian coordinates, right? And then we're going to work out basically what it does on the wave function, right? So this is now x, and then e to the plus I, dagger, plus I phi, j is Hermitian, so there's no dagger here, and this will act on psi, my wave function. Let me put a capital psi here. I realize that there's a problem with my notation, right? In this case, I should call it capital psi, because psi here doesn't mean this is an angle, right? So we have a slight problem. So let me call it capital psi. So this is a state. This is a state, not to be confused with an angle. Okay. Now we know what this does. What this does is that it does exactly what I said it will do here, right? So this is now x minus phi, and then epsilon dotted into x plus higher order terms, all acting on the state side. That's what this does. And then likewise on the right-hand side, I can now expand my exponential. Zeroth order is just the identity operator. First order is plus I phi j. Second order and so on. So higher order in phi. Psi. Okay. So we know that it's a Taylor expansion phi, so therefore we can equate both sides, right? But let me just Taylor expand this guy. So the first term is x psi, and then you start expanding this. So it's now this, you treat this as a small parameter, And then what you do is you take the exponent minus 5, and then this epsilon x, remember as a vector, will be dotted into the gradient of x psi plus higher orders in 5, and all of that will be equals to, this guy is x psi, and then we have plus I5 x j psi plus higher order terms. Okay, this will cancel that, and therefore what do we have here? We now have the order 5 terms must be equal, right? So what do we have? We have I, x, j. Okay, we have the matrix element in position space of the rotation generator between arbitrary state but in the position representation is now equals to minus epsilon dotted into x. The whole thing, this is a vector, this is a matrix times a vector, so it's a vector dotted into the gradient of x psi. Okay? But what is it? So what I'm going to do is I'm going to write this out a bit more explicitly. Okay, remember the epsilon, so this is now minus epsilon I j x j. That is the vector, that is the component, the I component of this guy, dotted into the I derivative. Right? So this, again, this guy, the I component is this object here, and then dotted into the gradient just means dotted into the derivative acting on x psi. Okay? But there are only two components in 2D, so we may as well write it out more explicitly. Okay, and in fact, what I'm going to do is I'm also going to multiply both sides by minus I. Minus, if I multiply by minus I here, it will be 1. Minus I will be plus I. And then let's work out what this will become. This will be, remember, it's going to run over I and j, but I and j are either 1, 2 or 2, 1 because they cannot be 1, 1 and 2, 2. I mean, they'll be 0, so there's no use considering them. So this will be just epsilon 1, 2, x 2 partial 1 plus epsilon 2, 1, x 1 partial 2. 1, 2, 1, 2, so 1, 2, and then 2, 1 be 2, 1, all acting on x psi. Yeah? So what do we have here? So we have 1, 2 is 1. Let me write it this way, minus I, and then, okay, one step at a time. So 1, 2 is 1, so it's x2 partial 1. This is minus, because remember epsilon 2, 1 is equals to minus epsilon 1, 2. So it's minus 1, x1 partial 2, all acting on x psi. And it's customary to pull out a minus sign so that I get 1, 2 to 1. So I get minus I, and then x1. Partial 2, remember, is just a derivative with respect to x2, minus x2 partial x1, all acting on x psi. Okay? And this, I hope, starts to look a little familiar. Why? If I package this in the following way, x1, and then I write minus I partial 2, and then minus x2 minus I partial 1, 1, 2 to 1, all acting on x side. This should remind you of something. Okay. So in fact, what you discover is that this is actually x. I can now bring it back inside x, position operator. Let me just write this down. Position operator 1. Right? Because this one acting on x gives you x1. And then this one is what? P2. The linear momentum operator P2. Right? So again, this acting on this will spit this out. And then you follow by acting this on this, it will give you minus I partial 2 minus x2 P1 psi. Right? So I started with what rotation meant. I applied on my position eigencat. I did a Taylor expansion on the left-hand side. And then on the right-hand side, I also did a Taylor expansion, but involving the operator with the generator inside. And now when I compact the order 5 terms and go through it, I discover that I can now put it back in terms of operator statement. Now I can now put it in terms of operator statement, which is that J is actually nothing but, in this representation, gotten from the position operator and the linear momentum operator. Right? And this is actually exactly why we call it orbital angular momentum. So if you remember, L angular momentum is what? Position cross momentum. Yeah? And then if you look at, for example, the third component of angular momentum, you will discover that it's exactly x1 p2 minus x2 p1. So in some in this case, I can call it L3, but I'm going to resist doing it because right now we're only in 2 dimensions. Okay? But it basically is. But for now, we're only in 2 dimensions, so I don't want to introduce the third direction yet. But this is where we're going. We're discovering that J is nothing but angular momentum. This is the momentum operator. So in fact, J is in fact x1 p2 minus x 2 p1 angular momentum. And I should call this the orbital angular momentum. Orbital because of this, the connection between this operator and the one that you've seen in classical mechanics. Right? This is how we first started learning angular momentum. It's in terms of r cross p or x cross p. Any questions for me? Yes.
What is what's that? The side.
Which one? What we discovered is that if you use symmetrical coordinates, then in fact you will discover the connection between what we did over here and what we did over there. Over here and over there. Okay, so maybe I'll write it in the following way. I think you will check. I don't know if this is your homework. Yeah, anyway, this will be probably your homework. You will discover the following, okay, that minus I x1 partial 2 minus x2 partial 1 acting on x side. Remember that this is what J is. There's an interpretation of this in terms of rotation. So therefore you have to be, J has to be flowing along the azimuthal direction. It has to be flowing strictly in terms of the angular direction. But of course in this form it's not very clear, right? It's often like that in physics. We want to understand things, the same thing, in different ways of writing it, because different ways of writing it gives us different insight, makes certain things clearer, but maybe some other things are not as clear. Right? So in this case, it makes it the relation between angular momentum you learn in classical mechanics and J, it makes that aspect clear. But then you somehow lose just by staring at this, you may not recognize immediately that it actually corresponds to translation in the angular direction, right? But if you know your calculus, you can in fact show that this guy is in fact minus I d phi x psi. Okay. Yeah. Yeah, you'll be able to show that this is actually equal to that. It's not obvious, right? You have to do some calculus to do that. But conceptually it should be clear, because it's just, this J is doing nothing but just translating it along the circle by a little bit. That's what it does. Okay, so now we are ready to say a few more things about the eigenstates with J, right? I've shown that the rotation operator is unitary, so the generator is Fermion. And we've worked out one representation, which is using this, the explicit rotation of the Cartesian position. But it turns out that there's something deeper going on, which I want to show you guys, which is that if you just look at the abstract eigenstates of J, you will discover something deeper than just rotations in space. Because after all, if that's all we're doing, then why don't we just rotate in space? Why do we have to insist on changing any basis? Okay? If that basis is good for everything, and why bother? So it turns out that we'll discover other kinds of bases that depend on the global structure of your states. So let me try to write that down and explain a little bit. And that will lead us to a deeper sense of what rotation is, spin is, what spin in angular in quantum mechanics means. Is a deeper concept that doesn't always have a very intuitive. It's hard to give an intuition to it because of that. So we'll discover it very soon. And then later on we'll see it again in the three-dimensional situation. Yeah. Do I need this? No, I think I don't need this. So I'm going to erase this as well. Okay. Yep. So, here's the game, right? So now we're going to consider the eigenstates J. And remember, again, because J is Hermitian, and this we've proven, therefore we know that J has to have a complete. J has to span, it has to span the Hilbert space, right? Whatever system that we're working with, the eigenstates of J must span the physical Hilbert space because it's Hermitian. So, but we also know the position basis, right? That's actually how we started with rotations. Without the position basis, we wouldn't know what we're doing. So let's consider the following. So let's stick with the psi. Okay, so psi, let's do the following. Let's now rotate psi by a full revolution, e to the minus 2 pi j on psi, and then we acted on m. Okay, so there are two different ways to think about this. One way is to recognize that this is just going to rotate it by 2 pi and acted upon the eigenstate of j. The other way to think about this is psi, and then e to the plus I 2 pi j. J, again, is Hermitian, so there's no j dagger here, acting on m. Okay, but remember, this is an eigenstate of j, so I can Taylor expand term by term, and this is just going to give you e to the I 2m, oops, I'm sorry, 2 pi m psi m. Sorry, I forgot again that, no, these are all angles. Yeah. Okay. So we're going to discover something about these eigenvalues. And that's the key point. Did I make a mistake again? Oh, thank you. Yes, thank you. Yeah. So now we'll see the crucial thing, and this is why I say it depends on the global structure of the rotation group, is what kind of boundary conditions. Right, so if you're taking an undergraduate quantum mechanics course, you should already know that in quantum mechanics, the boundary conditions are very important for determining all kinds of things, right, including the energy levels. Right? So probably you guys have spent a lot of time solving one-dimensional problems, and then when you match the boundary conditions, they will give you your energy eigenvalues. Right? So we don't, I'm assuming you've done quite a bit of that. That's why we don't do that here in this course. But rather, I want to emphasize the deeper conceptual issues regarding symmetry. But of course, it is important to know these things. And so this is one example. So what do I mean by that? So for example, you might think that the most natural way to do it, so number one, so example one. You might think that this is the most natural thing to do. Psi plus 2 pi must, of course, equal to psi. Right? You might think that, well, how else can it be? You better come back to yourself, right? You're on a two-dimensional plane, so if you come back to yourself, you better get back the same state. But remember, in quantum, there are different ways to motivate this, but in quantum mechanics, remember that the state itself is not a sharp observable. It's only the square of the amplitude that becomes a probability. right? So all the eigenstates are only defined up to an overall phase because of that. There's no way to measure the individual phase of the eigenstate, because all I require is that the operator, the observable, acting on the state gives me an eigenvalue. But if I multiply it by a phase, it doesn't change it, right? And I square the amplitude, the phase goes away. So there's no way in quantum mechanics at least to determine the phase. You know, maybe some years from now, you guys can come up with a new quantum mechanics where the phase matters somehow, right? Only in interference, only when you are interfering, superposing different states, then the relative phases matter. Right? The relative phases matter, but even then it's the relative phases. Anyway, so in general, the eigenstate phase is not determined. So in general, you might expect that psi plus 2 pi actually might give you a phase, because you can't measure it anyway. At least not directly like that. Like I said, you know, it will show up. It may show up in an interference pattern, in an interference kind of experiment. But and we'll talk a little bit about this actually in later on in this class for fermions. But you know, so because of that, you should expect that it's not completely trivial. Right? This is the deeper part of rotations that you wouldn't otherwise think about. If all you think about is just two-dimensional rotations, where cosine and phi, cosine phi, sine phi, and so on, you wouldn't arrive at this position, this place. But now, because we're doing quantum mechanics, your system is not just a bunch of coordinates anymore. Your system is actually an abstract state. And in this case, we're using the position basis to describe it. There's this question now, what is the right boundary condition? So let's try this for now, okay? So let's try 1. And let's look at the consequence of this. So if this is true, then psi plus 2 pi m equals to psi m, right, because of this, because of 1. And that must be equals to e to the I 2 pi m of psi m. And there we go. So we discover that e to the I 2 pi m must be equals to 1. So this, remember, is a complex number on the unit circle, which means that m must be an integer. 0, plus minus 1, plus minus 2, plus minus 3, and so on. Okay, so you see, the importance of the boundary condition is that it has now fully determined what kind of eigenvalues your J will have. Right? Remember, these are the eigenvalues of J. So now you discover that these are the integer spin. And I claim later on, later on, you discover that there's a relationship between this particular representation. The orbital angular momentum will take on integer spin. Okay, we're not quite there yet, but we'll be able to show that it is true. Actually, the best way to do it is to convert it into symmetrical coordinates, right? So remember that this is, I'll get to that in a little bit. But it's not the only situation that occurs in nature, it turns out. Okay, so there's actually a second possibility. Let me not call it example because it actually shows up in nature. The second example is the following. The second example is that you don't require that it comes back to itself, but it actually comes back to negative of itself. Okay? And so when that happens, what happens is that you get psi plus 2 pi acting on m is now minus psi of m, and this is now e to the I to m pi psi m. Okay, which means e to the I 2 pi m must be equals to minus 1. But that's definitely different from this guy. This tells you you need to make complete revolutions of the circle. Right? Remember that e to the I theta is somewhere on the unit circle. So this tells you that you must always end up here. This tells you you must end up always here. This tells you that you must always end up here, which means that you must always go through a half integer multiple of a full rotation, right? Odd number of pi's. So odd numbers of pi. So yeah, that's exactly right. So 2m must be odd. Yeah. Otherwise, you won't end up here. If you have even, it means you come back here. So what does that mean? That means that m itself must be 1 over 2, 3 over 2, actually plus minus 5 over 2, plus minus 7 over 2, and so on. It's very strange, how do we get here, right? And so this turns out to be, in fact, the beginning of Fermions. These are electrons, the elementary particles in nature that have behaved like that. Electrons, muons, taus, neutrinos, quarks. These are the elementary particles, but there are also composite bodies like these are elementary. The composite guys also have fermions. Protons are spin half, neutrons are spin half. The higher spin as well. If you guys are interested in this kind of things, you can look up the pdg.lbl.gov. That is a whole review book. It's a little dense, a little difficult to understand, but they compile all the known hadronic particles that has ever been observed in accelerator experiments. And you can find there's a whole zoo of particles that you can produce. But mainly, they are mainly built out of quarks. Right? The quarks can bind together with gluons to give you these fermionic higher spin particles. But they're not elementary. The elementary ones are what I written there. They're the leptons, leptons and quarks. So this is the discovery that we have made in nature since about maybe 100 years. I don't know how when was but Goldsmith and I forgot the other guy's name now. It's written in Weinberg. They both postulated there must be this additional degree of freedom that the electron must have in order to account for atomic spectrum. Right? So when we get to it, I'll say this again. But I'm now looking at it from hindsight. Right? Usually it's like that in physics. We work very hard. We do a lot of gas work to arrive at where we are. But then once we understand things, we no longer explain things the way the history went, right? So this is what I'm doing basically. I'm telling you that spin fundamentally comes from studying the properties of the rotation group, how rotation works, but not in the real space, but on the Hilbert space of the quantum system. And by imposing different boundary conditions, you find that you get, this is called the boson. These are the bosons. And then for the half integer spin, we call it the fermions, right? And so we discover that just by studying the rotation group, you get just different types of representations. You get different types of possibilities of the eigenvalues of J, right? And of course you can cook up other boundary conditions as well, right? But I won't go there. I just want to show you these are the two types that definitely do occur in nature. Of course you can ask, right? Why doesn't nature use other representations? Right? There is a question of this. Just like if you study relativistic quantum field theory, you will discover there are also representations of the Lorentz group that somehow nature doesn't use. You know, these continuous spin representations. There are in fact there's something called continuous spin. Why doesn't nature use them? Maybe it doesn't work. Maybe there's a pathology involved. But who knows? You know, it's not a very well. There's a little bit of work done there, but it's not a very well studied topic. Yeah, nature does what it wants. Right? We only can attempt to understand it. Okay, so that is, I think, let me just check, the main part of two-dimensional rotations that I want to talk about. So the last part. Okay, so let me finish with this one, and then on Thursday we can continue on something else. So let me finish. I'm almost running out of time, but let me finish this part because I want to connect it back to the Fourier series, right? So this, in fact, the bosonic case is in fact related to the Fourier series that we have been discussing. And the reason is clear, because in the Fourier series, we assume that our function is continuous across the domain, right? So when you jump from phi to phi plus 2 pi, we assume that the function is continuous, and therefore that's what the Fourier series is saying. But in this perspective, we view it as a change of basis from the position basis in terms of the angles to the eigenstates of the rotation generators, right? So any state, now I introduce capital phi, must be expandable, and will run from minus infinity to plus infinity in integer steps in terms of these eigenstates. Okay? And what you will discover is that if I write this in terms of the position eigenstate, then this will give you phi, m psi. So these are just numbers. This is like the analog of the Fourier coefficient in Fourier transforms. But now you are doing Fourier series, so these will be discrete indices. M is a discrete index. But what is this guy? You will discover that in fact this is in fact the analog of the plane wave. And let me write it down and try to motivate where it comes from. This is in fact e to the I m phi over square root 2 pi and capital psi. Okay. How do you know this? Remember that we can use the fact that J phi m is equal to minus I d phi. Remember, this is your homework. We have derived the fact that this is x1 minus x1 p2 minus x2 p1, x1 p2 minus x2 p1, yeah. But in your homework you will use symmetrical coordinates and show that this is actually just a partial derivative with respect to phi. But at the same time, you know that this is the eigenvalue, eigenvector of j, so this will just be m, phi m. And if you look back, this is exactly how we derive the Fourier transform, except that these were continuous case. Right? If you remember, this was continuous case, but we also had a derivative over here. So what you see is that phi m must solve this differential equation, but luckily this is just a first order differential equation, so you can easily recognize that this is e to the minus I, sorry, e to the I m phi, because when you add minus I phi on it, you spit out an m, right? And then the only other thing is there's a normalization, right? So there's a c, there's a constant here. But what we're going to require is you're going to require that m phi squared be normalized to 1 when you integrate over one circle. Then what you see is that basically c squared times 2 pi is 1, right? Because this guy squared is just c squared, because the phase will drop out, and therefore c is chosen to be 1 over square root 2 pi. Okay? And that's how you discover that. This guy is just given by this and this, right? C e to the I m phi, but c is given by 1 over square root 2 pi because of the normalization. So finally, let's now write down in this representation. In this representation, we now discover another way of writing the rotation operator. Okay? So instead of writing it in terms of these, so there are different ways of writing it. So let me just write it down. So there's one way of writing it, which I think I wrote it the last time, which is the following, right? You take phi plus psi, and then psi d psi. That's one way of writing it. You take the original cat and you rotate it by this much, and this is the old cat and the new cat, right? Sorry, old basis and new basis. I mean, but if you use the first condition over there, what you discover is the following. You discover that you can use this guy to write it as d phi, and you can now express it in terms of the completeness relation. You can use the completeness relation, and you can write it in the following way. This is